let's look at some examples of singularities. So the first one, 1 over z plus 1. Well, this is a simple pole. One way of thinking about it is that, okay, it actually is a Laurent series already with z naught equal to minus 1. So this has simple pole at z equals minus 1. Another way of looking at it is that 1 over this function is z plus 1. That has a simple 0 at z equals minus 1. It's equal to 0 when z equals minus 1. Okay, what about this? E to the z over z to the 4. So obviously when z equals 0, this is 1 and this is 0 on the bottom. Clearly, this on the bottom is a 0 of order 4. You've got 1 over a 0 of order 4, that's a pole of order 4. So this is a pole of order 4 at z equals 0. What about e to the 1 over z? Well, I actually mentioned e to the 1 over z a bit earlier. This one is a bit strange. As I said before, with these previous examples, it's fairly obvious that when as z tends to minus 1, you're going to get infinity, or z tends to 0, you're going to get infinity. In this case, it really depends. Okay, we obviously have a problem at 0, but it really depends whether z tends to 0 from the left or the right. If z is negative and tending to 0, then you'll end up with e to the minus infinity. If z is positive and tending to 0, you'll end up with e to the plus infinity. So it doesn't have a definite limit as z tends to 0. So that suggests it's going to be an essential singularity. But we can actually see this explicitly if we just expand it using the definition of the Taylor expansion of e to the 1 over z, e to the z. So now we're going to have 1 plus normally a z over, so the expansion of e to the z is 1 plus z squared over 2 factorial and so on. Now replace the z by 1 over z and we have this. And so on. So this never ends. This is B1, this is B2, this is B3, and so on. So we'll have infinitely many B's. It definitely is an essential singularity. So this clearly has a 0 of order 3 at z equals 0. Because this z cubed is a... sorry. The bottom of this, I should say, the bottom of this has a 0 of order 3 at z equals 0, which means overall this function has a pole of order 3. So z equals 0, pole order 3. And then the denominator has this 1 plus z squared. So we can factor that 1 plus z squared is equal to So, well, okay, that's maybe a long way of doing things. But anyway, this is going to have, this has roots at z equals, z squared equals minus 1, so z equals plus or minus I. So it's going to have simple zeros at, this has simple zeros at z equals plus or minus I. Overall, this function is going to have simple poles at z equals plus or minus I. So next one, sine z over z minus pi. Okay, this is a slightly more interesting example. Now the bottom has a 0 of order 3 at z equals pi, but this doesn't have a pole of order 3 at z equals pi, because on top sine z has a 0 of order 1 at z equals pi. Okay, when z equals pi, we've got sine pi is 0. Okay, so we've got a 0 of order 1 divided by a 0 of order 3, which overall gives us z equals pi, we have a pole of order 2. So it's basically, it looks like a pole of order 3, but because of this, it reduces it by 1. Next example, sec z. So sec z is the same as 1 over cos z. Cos z, remember, has zeros at same place as cos, but you multiply by I. So it has cos z has simple zeros at these locations, which means that 1 over cos z, sec z, will have simple poles at these places. Well, you should always write what n means, just any integer. So 1 over 1 plus e to the z. So this is going to have a simple pole whenever this thing here is 0. So we want, when is e to the z plus 1 0? Well, we know that e to the I pi is minus 1. So it's basically when z is equal to I pi. But remember, e to the z is a periodic function with period 2 pi I. So it's actually e to the I pi plus I 2 pi n I. In other words, when it's 2n plus 1 pi I. At those places, e to the z plus 1 has simple 0, which means 1 over 1 plus e to the z has simple poles at those locations. Final example, e to the z. E to the z has no singularities in the complex plane. That's all there is to it.